Good day and welcome to today's lesson. In today's lesson, we'll be looking at photoresistors. What we have in front of us here is an example of a photoresistor. A photoresistor, also known as a light-dependent resistor, is a type of resistor whose resistance changes with the intensity of light falling on it. It is a sensor that detects light and converts it into a change in resistance. Now that we know what a photoresistor is, we will look at the working principles of a photoresistor, and they are as follows. The first thing is the semiconductor material. Photoresistors are made from a semiconductor material, typically cadmium sulfide, which exhibits high resistance in the absence of light and low resistance when exposed to light. We will see this when we look at a practical example whereby we interface the photoresistor you see in front of you with an Arduino Uno. The second thing is light absorption. When light falls on the surface of the photoresistor, photons from the incident light are absorbed by the semiconductor material. This absorption causes an increase in the number of charge carriers, meaning an increase in electrons within the material. The third thing is electron flow. The absorbed photons excite the electrons in the valence band of the semiconductor, enabling them to move across the band gap to the conduction band. This movement of electrons reduces the resistance of the material, allowing current to flow through it. The fourth thing is resistance variation. The resistance of the photoresistor is inversely proportional to the intensity of light falling on its surface, meaning that as the intensity of light increases, more electrons are excited, reducing the resistance. Conversely, in the absence of light, the resistance increases since there is minimal electron excitation. Let's look at a visual representation of how this works. Excitation of electrons from the valence band through the band gap to the conduction band. In the absence of light, we observe the following. No photon excites the electrons in the valence band, thus no electrons move through the band gap to the conduction band, hence the high resistance of current moving through the semiconductor. In low light intensity, we observe the following. Photons coming from the incident light are absorbed by the semiconductor material, resulting in the excitation of electrons on the valence band, causing them to move through the band gap to the conduction band. Hence the minimum resistance of current flow through the semiconductor. In high light intensity, you observe the following. We have more photons coming from the incident light, which are absorbed by the semiconductor material, resulting in more electrons moving through the band gap to the conduction band, hence the low resistance of current moving through the semiconductor material. Overall, photoresistors provide a simple and cost-effective means of detecting and measuring light levels in various electronic and electrical systems. They are widely used in applications such as automatic street lights, camera exposure control, solar panels, and light intensity meters. In this course, we'll be building a light intensity meter, which could be used in agriculture to track the amount of light that plants get from the sun throughout the year, helping farmers understand which plants are affected by light intensity, which in turn affects crop yield. The first thing we will do is to connect the photoresistor to Arduino Uno. We do that by firstly connecting the signal pin of the photoresistor to analog pin 0 of the Arduino. We then connect the VCC pin of the photoresistor to the 5V pin of the Arduino Uno. Lastly, we connect the negative pin of the photoresistor to the ground pin of the Arduino. Now that we are done connecting all the photoresistor pins to the Arduino, we will continue building the light intensity meter. For this circuit to work, we will code up the logic in Arduino IDE and upload the code into Arduino microprocessor. Now let's connect the Arduino Uno to the PC and start coding.